Today on Macaulay Math, we're talking about concavity. Intro. Okay, good day. I'm Professor Macaulay. This is Math 200, Calculus 1, Lesson 16 on concavity and the second derivative test. Our goals for today. We're going to determine the intervals on which a function is concave upward or concave downward. We're going to find points of inflection, and we're going to apply the second derivative test to find the relative extrema of a function. The concept of concavity describes how the rate of change of a function is itself changing. That may seem confusing at first glance, but consider the position function. The first derivative of the position function with respect to time is a velocity. The second derivative of a position function with respect to time is the acceleration function. If the acceleration of a function is getting smaller but is still positive, then the velocity is still increasing just at a slower rate. Concavity also has applications in astronomy by calculating Doppler shift estimations. Generally, concavity is used in optimization and finding optimal solution for functions. The point of inflection is the point where a function is either increasing or decreasing at the greatest rate. Let's start with a definition here. Concavity and the second derivative test. Let f be a function that is continuous and the second derivative exists on the open interval from a to b. Number one, if the second derivative of x is greater than or equal to 0 for all x in the open interval a to b, then f is concave up on the open interval from a to b. And if the second derivative of x is less than 0 for all x in the open interval from a to b, then f is concave down on the open interval from a to b. Let's look at a quick demonstration here. Here we have a linear function that is increasing. Thus, we know that the values of the first derivative are positive over the open interval. Since the function is increasing at a constant rate, the second derivative has value equal to 0 over this same interval. If the function looks like this, it is now concave up and is still increasing. Thus, the values of the first derivative is still positive, and since it is now concave up, the value of the second derivative is also positive. Finally, if the function looks like this, the function is still increasing. So the values of the first derivatives are still positive, but the function is now concave down, so the values of the second derivative are now negative. Points of inflection. For the twice differentiable function f and the point x equals c in the domain of f, if the second derivative of c is equal to 0, or if the second derivative of c does not exist, then f of c may be a point of inflection. There is a point of inflection when the function changes its concavity at that point. A sign chart may be helpful to determine the concavity of a point. A sign chart is not enough evidence to prove the concavity of a function. So what does this point of inflection look like? Well, if we draw just a simple graph in here, and we have a function that comes to this point, and this curve is concave up, and then at a point it starts to level off, it is increasing everywhere, but the concavity changes from concave up to concave down. So here at 0, 0, we have a point of inflection. Sometimes known as the point where the function is increasing or decreasing at the greatest rate, sometimes known in business as the point of diminishing returns. Second derivative test. A second method for finding extrema. Let f be a function such that f prime is 0 and the second derivative of f exists on the open interval containing x equal to c. Number one, if the second derivative of x is greater than 0, then f has a relative minimum at c f of c. And if the second derivative of x is less than 0, then f has a relative maximum at c f of c. So what does that mean? Let's draw in a function that has a relative maximum and a relative minimum. So we know that there's a potential extrema because at this point right here, there will be a horizontal tangent line. So we have a point C where the first derivative of C is equal to 0. And again, right here, we have another point where that first derivative is equal to 0. Now, it says if the second derivative of x is greater than 0, so concave up, then we know that we have a relative minimum. So look here. Here, the function is concave up. We have a relative minimum. If the second derivative is negative, then f has a relative maximum at this point. So in this portion of the graph, the function is concave down, so our possible extrema point has to be a relative maximum. Let's tie some things together. Let's draw some pictures. Situation 1. If I were to say that we have a function where the first derivative is positive and the second derivative is positive, then the first derivative says that the function is increasing, and the second derivative, being positive, says that it's concave up. So if I want to draw in a function from a to b on this closed interval that meets these two criteria, then it would look like this. First derivative positive, it's increasing. Second derivative positive, it's concave up. The next situation, the first derivative is positive and the second derivative is negative. So if we draw in the same type of diagram here, the first derivative being positive means that it must be increasing. With the second derivative being negative, it must be concave down. So there's an increasing function that is concave down. The next situation, the first derivative is negative and the second derivative is positive. So on a to b, the first derivative being negative means that this function is going to decrease as we go from left to right. The second derivative being positive means that it's going to be concave up. So we'll have a graph that could possibly look like that. And the final set of criteria, again, we have a closed interval from a to b. The first derivative is negative. That's going to tell me that it is decreasing over that interval. And the second derivative being negative, that means it's going to be concave down. So a graph would have to look something like that over that interval. Next example. Find the points of inflection and discuss the concavity of the graph of the function f of x equals 2x to the fourth minus 3x squared plus 3. And so the first thing we want to do, find the first derivative. And so f prime of x, 4 times 2 is 8. X, reduce this by 1 to give me a third. 2 times 3 is 6. And the derivative of constant is always 0. Now, this is the first derivative, so it doesn't find concavity. It finds slopes of the tangent lines and whether a function is increasing or decreasing. So to get to concavity, we now need to find the second derivative. And so f double prime of x is going to be 3 times 8 is 24, so I'll have 24x squared minus 6. And the points of inflection may exist wherever the first derivative is equal to 0. It is also going to be the values of x where it can change concavity. So we're going to set this equal to 0. And so I have 24x squared minus 6 equal to 0. 24x squared equals to 6. X squared equals to 6 over 24, which is a quarter. And then x will equal plus or minus the square root of a fourth, which is plus or minus 1/2. All right. So I'm going to come over to this number line to find my intervals. And so at negative 1/2, I have a value. And then at positive 1/2, I have a value. Okay. So we just need to pick a value somewhere in this interval from negative infinity to negative 1/2. And I'm just going to pick, say, negative 10. And we're going to put it into the second derivative. And if it's positive, it's going to be concave up. And if the result is negative, it'll be concave down. So when I plug in negative 10 squared is 100. 100 times 24 is 2400. Minus 6 is going to be positive. So we have a positive value here. All right. Now, I need a value between negative 1/2 and 1/2. 0 is very convenient because 0 squared is 0 times 24 is 0. Minus 6 is negative. So over this interval, the values of the second derivative are negative. And then if I pick 10 on the third interval here, I'll have 10 squared is 100 times 24, 2400 minus 6 is still going to be positive. So here I know that my concavity is going to be concave up on this first interval, which starts at negative infinity and goes to negative 1/2, and then it will also be concave up from 1/2 to positive infinity, and then it will be concave down from negative 1/2 to positive 1/2. So let's write that out. So f is concave up on negative infinity to negative 1/2 unioned with 1/2 to positive infinity, and concave down on negative 1/2 to positive 1/2. Now we need to talk about our points of inflection. We will have points of inflection at negative 1/2 and positive 1/2 because it changes from concave up to concave down and from concave down to concave up at negative 1/2 and positive 1/2. So all we have to do is plug in those values. So let's do that. And for right now at decimals, we're just going to use the scientific calculator. So we're going to take and we're going to plug back into the original. So what we're going to do is we're going to go 2 times 1/2 raised to the 4th, and then it'll be minus 3 times 1/2 raised to the 2nd, and then if we want to have that as a decimal or as a fraction, we can put that in. So it'll be 8/19, and that's going to be for the half. So, and I apologize, it's 19/8. And then here's the thing: if I would change the half to negatives, it'll be to the 4th power and to the 2nd power, and when I take a negative to a even power, I'll get a positive value out, so I don't need to really do that a second time. It's going to be 19/8 again. So those are our points of inflection. Now, just as a check, let's take a look at it in the graphing Desmos calculator. So we'll go f of x is equal to 2x raised to the 4th minus 3x squared plus 3. And we can see that if I, at about right here and about right here, we have points of inflection. Now, what we can do is we can go make a table, and you'll see it, and we'll go in here. We'll zoom in. If I make this f of x1, make a table here. If I go negative 1 divided by 2, and I go positive 1 divided by 2, and we zoom in, you can see that it's definitely changing from concave up to concave down at our 2 points at a half and at negative half. All right, next function. F of x equals sine x plus cosine x on the closed interval from 0 to 2 pi. So first, let's take that first derivative, and the derivative of sine x is cosine x, and the derivative of cosine is negative sine, and then we'll take that second derivative, and the derivative of cosine is negative sine, and the derivative of sine is cosine. And so what we'll do is we're going to set this equal to 0. And so I'll have, let's see here, negative sine x minus cosine x equals to 0. So our possible points of inflection are wherever this expression is equal to 0 or undefined. Now it's never going to be undefined, but if I move the cosine over and I get negative sine x equal to cosine x, well, where's this expression going to be true? This expression is going to be true when the cosine value and the sine value have the same magnitude, but they have different signs. Now, if I remember on my unit circle, it has the same magnitude at these 4 points. But it's not going to be this point or that point, because at that point they have the same signs. So we are looking for this point right here and this point right here, because they'll both be square root of 2 over 2, and one of them will be negative and one of them will be positive. So our only possible points of inflection are going to be at 3 pi over 4 and 7 pi over 4. So I'm going to use a number line to get an idea of what values we might possibly get. Okay, so let's see here. 3 pi over 4 and 7 pi over 4. Let's try and make it easy on ourselves. Let's choose something smaller, or yeah, a little bit smaller than 3 pi over, because we have to stay in 0 to 2 pi as our interval. So let's pick pi over 2, all right? And so pi over 2, the sine is positive 1, the cosine is 0. So I get negative and plus 0 is going to make this one negative. And then let's pick pi. That'll make it easy if I pick pi. That's definitely between 3 pi over 4 and 7 pi over 4. So let's pick pi. The sine of pi is 0. The cosine of pi is negative 1. So negative 1 is going to be positive. And then 7 pi over 4 is really close to 2 pi. And let's see. So let's go 11 pi over 6. So the sine of 11 pi over 6 is going to be negative 1/2. And the cosine of 7 pi over 6 is square root of 3 over 2. And so negative, that makes it positive, but it's still smaller than the cosine magnitude. So this is going to be negative. So I am going to have points of inflection at 3 pi over 4, comma, and 7 pi over 4. Got to find the y values yet, but you do that at the original function. So the sine of 3 pi over 4 plus the cosine of 3 pi over 4. I'll have the sine is going to be square root of 2 over 2, and the cosine will be negative square root of 2 over 2. So I'm going to get 0 there. And I have a feeling it's going to be the same when I do this other one. So the sine of 7 pi over 4 plus the cosine of 7 pi over 4. The sine of 7 pi over 4 is negative square root of 2 over 2, and the cosine is positive square root of 2 over 2. So I get 0 again. So both of these points of inflection are going to be at 0. And then the concavity, I only have 3 intervals. And so where the values of the second derivative are negative, it's going to be concave down. And where the values of the second derivative are positive, it's going to be concave up. So f is concave down on 0 to 3 pi over 4 unioned with 7 pi over 4 comma 2 pi, and is concave up on 3 pi over 4 to 7 pi over 4. Now, if we wanted to, we could check that fairly easy. Just go to f of x equals sine x plus cosine x. I'll get this. And from 0 to 2 pi is right here. So concave down until I get to 3 pi over 4, 0. And then it becomes concave up. And then from 7 pi over 4, 0 to 2 pi, it's going to be concave down once again, which is what I have. All right, last one. This one isn't a whole lot of actual calculations, but it is, we're drawing a picture with the following characteristics. So at f of 0, it's going to be equal to f of 2, and it's going to be 0. So those are actually points on the graph. So I'm going to fill in the dots there. So at 0 and 2, it's equal to 0. So now so the second statement here says that the first derivative is greater than 0 for values of x that are less than 1. So from 1 down, this thing has a first derivative that is going to be greater than 1. So we know that this function is increasing on the interval negative infinity to 1. Because for all values of x that are less than 1, the first derivative is going to be positive. Here it says the first derivative at 1 is equal to 0. So we have an extrema at x equal to 1. Here it says the first derivative is going to be negative for values of x that are greater than 1. So this says that it is decreasing on 1 to positive infinity. And it says that the second derivative is less than 0 and without any constraints, so everywhere else. So this thing says that f is always concave down. All right, now, since it's increasing on the left side of 1 and decreasing on the right side of 1, the first derivative test says that I'm going to have a relative maximum at 1. And so it's increasing until I get to 1, decreasing when I go from 1, always concave down. I've got a 0 at 0 and 2. That is going to be a valid graph. And there are multiple correct answers, but that one will be good enough for this class. All right, folks, that's all I've got for today. So the Star Wars fun fact of the day. As of this recording, C-3PO, acted and voiced by Anthony Daniels, has been in every Star Wars movie with the exception of Solo, A Star Wars Story. And here we see him in Episode 1, The Phantom Menace, Episode 3, Revenge of the Sith, and Episode 5, The Empire Strikes Back. Arguably the best Star Wars movie. All right, that's all I got for today, folks. Have a great day. Goodbye.